Imagine a glowing airport in the middle of the sea, where the runway lies close to the breath of the waves. Above it are steel, glass, and aircraft. Below it, soft mud is quietly answering back. This structure was built offshore, on a massive artificial island raised by human hands. It cost tens of billions of dollars, yet still cannot stop the ground beneath from deforming. In some places, the island has sunk by many meters, and that movement is still tracked year by year. By ordinary logic, an international airport should not rest for decades on ground as soft as a wet mattress, because every ton of reclaimed soil squeezes water from clay more slowly than human eyes can notice. If monitoring stopped, a small tilt could quietly spread through the terminal floor. If elevation were not adjusted, seawater and storms would gain more advantage at the island edge. If maintenance were neglected, an airport island could turn from a miracle into a burden every typhoon season. Yet aircraft still land, passengers still pass through, and the terminal still glows every day. It survives not by staying motionless, but by being measured, lifted, repaired, and adapted. That steel table still stands on a wet mattress because someone keeps adjusting each of its legs. This is Kansai Airport, an aviation island negotiating with mud, seawater, and time. The real question is not why it is sinking, but why it continues to operate. The problem began in a large city, where the old airport was trapped among homes and noise. Expanding on land meant touching residents, land prices, complaints, and political limits. So the sea appeared as a rare, empty space between the demand for flights and urban life. Offshore, aircraft could operate around the clock while placing less noise over residential areas. But that empty space was not empty land. It was bay floor, deep water, and soft clay. The geology there did not behave like hard rock, but like a slow body being pressed downward. For engineers, building here was not just placing foundations, but having a dialogue with time. Before any runway existed, a seawall had to hold the shape of the future island. Rock, sand, and soil were carried out to sea, layer by layer, as if creating ground from nothing. Each layer of fill raised the island higher, while sending more pressure into the deep mud. That was the first paradox. To escape the city, the airport had to enter harder geology. Japan did not lack engineering skill, but Osaka Bay did not offer an easy foundation. The younger soil near the seabed was softer, while deeper, older layers could still compress. Clay does not drain quickly, so its response arrives later than human decisions. A construction decision can be completed in a few years, but the ground answers over decades. So Kansai's design did not only need to carry loads, it had to accept settlement. That was not failure from the beginning, but a natural condition built into the problem. But accepting settlement does not mean knowing exactly where it will stop. Beneath the sea, there is no perfect foundation, only one understood well enough to manage. From that moment, Kansai was no longer an ordinary airport, but a living geotechnical experiment. The engineers' first response was not to deny the mud, but to help it drain faster. Sand columns were driven downward like tiny escape routes for water trapped inside clay. As water drained out, soil grains moved closer together, and the ground began to grow firmer. A process that would normally take a very long time was forced to happen earlier, before the airport was complete. That was how humans tried to make the ground settle while they could still control it. But not every layer beneath could be treated by driving sand into it. The deeper clay layers were too thick, too complex, and too difficult to reach directly. So the strategy was not only reinforcement, but predicting the part that could not be reinforced. The airport was designed with the idea that the ground would keep moving after opening day. An ordinary structure wants to stand still. Kansai had to learn to stay stable while sinking. Runways need to be flat, terminals need to be level, but the island below does not promise equal treatment. So engineers treated uneven settlement like a tiny saboteur. Even a small difference can jam doors, tilt floors, or shift the way structures carry loads. The solution was not to make the terminal invulnerable, but to make it adjustable. Here, flexibility is not a weakness. It is the condition for a structure to live long. At the same time, the seawall must protect the island from waves, while the foundation learns to carry weight. An offshore airport therefore needs two foundations, a physical foundation and an operational foundation. The physical foundation resists weight. The operational foundation resists surprises, deviations, and aging. This is when the steel table began to have legs that could adjust to the wet mattress. But the better the airport adapts, the more it depends on a monitoring system that must never fall asleep. When the airport entered operation, ground settlement stopped being a construction problem and became a work schedule. Measurement points were placed across the island to turn the slow movement of soil into visible data. No one can see clay compressing, but sensors can record every small change. That data shows where the ground is lowering quickly, where it is slower, and where intervention is needed. Like doctors listening to a heartbeat, operators listen to the settling rhythm of the artificial island. The numbers do not appear on the runway, but they decide when the pavement must be raised again. For the terminal, the story is even more delicate, because passengers need everything to feel normal. Beneath that clean floor are columns, hydraulic jacks, and steel plates used to correct tilt. When a column is lower than needed, it can be lifted with hydraulic force. Then a steel plate is inserted, like shimming a giant table. The difference is that this table carries the terminal roof, walkways, and daily human flow. The system must also remove rainwater from the island faster than it can cause trouble. An artificial island has no natural hills, so drainage must be part of the design. At the same time, the seawall must be tall, strong, and tight enough to keep waves from turning the runway into a canal. An airport on land worries about the ground. Kansai must worry about both ground and sea. Individual parts are not enough. Strength lies in how they are connected into a chain. If one link weakens, the rest must detect it before passengers notice. That is why Kansai is operated like a body. Measure, respond, repair, then measure again. The airport still appears normal precisely because the abnormal behind it is being managed. In this story, stability is not a condition, but a repeated task. A day without incidents does not mean the ground has stopped moving beneath aircraft wheels. The more sophisticated the system becomes, the easier it is to forget that it is fighting a very slow process. Beneath every flight is a quiet examination between geology, machinery, and people. This is why Kansai is not just transport infrastructure, but a living geotechnical system. Once the system is formed, the next question is, what is the clay really doing down there? Settlement begins when new weight is placed on clay that contains more water than it appears to hold. At first, water in the soil carries part of the pressure, like a wet sponge pressed by a hand. But water does not want to stay forever. It searches for escape through extremely tiny gaps. When water leaves, the soil grain framework carries more load, and the entire layer shrinks. That is consolidation, a technical word for soft soil losing water and becoming lower. The frustrating part is that clay drains very slowly, so consolidation does not end on the opening schedule. With sand or gravel, water can drain quickly. With clay, every drop moves through a maze. That is why two soil layers under the same load can settle at completely different rhythms. Uniform settlement only lowers the island. Uneven settlement is what distorts structures. A runway can tolerate uniform settlement, but it cannot tolerate sudden steps or breaks. The terminal is the same. If columns descend differently, the floor can bend slightly but dangerously. That is why Kansai does not only measure island elevation, but every important point. The real map of the airport is not only on the surface, but also in depth. At that depth, the island's weight spreads outward, not straight down like a simple pile. The wider and heavier the island becomes, the more it awakens deeper soil layers. This is what makes prediction difficult. Deep soil is not uniform like a laboratory material. A layer may be harder in one place and softer in another, even if the surface looks identical. A small error in deep soil can become a large difference after many years of loading. So settlement is not a fall, but a long answer from the material. On the surface, people see aircraft. Beneath the surface, pressure is redistributing responsibility. Piles and foundations help transfer loads, but they cannot erase the movement of the entire island. If the whole island lowers, the structures above must move with it or be lifted where needed. Jack-up work does not stop settlement at its source. It corrects the geometric consequences it leaves behind. Like adjusting table legs, engineers do not instantly make the mattress firm. They keep the tabletop level. For runways, elevation correction usually happens through resurfacing, leveling, and pavement maintenance. For seawalls, the issue is not only height, but the remaining safety margin before storms. As the island gradually lowers, the same wave becomes more significant against the edge of the structure. So ground settlement and flood protection cannot be separated in an offshore airport. Soft ground does not destroy an airport with an explosion, but by gradually shrinking its safety margin. That margin is the distance between normal operation and failure, between heavy rain and true flooding. As extreme weather grows stronger, the old safety distance may no longer be as wide as before. So engineers do not only ask how far the ground will sink, but how high the sea will rise. The problem becomes combined. The ground below is slow, while the sea outside may be faster. In every maintenance cycle, operators are buying more time for a structure that does not stand still. The strange thing is that the more one understands the mechanism, the less simple this airport appears. It is not sinking because it was forgotten. It is sinking because physics continues after the opening ceremony ends. And that physics does not care how much the airport cost or how beautiful it looks. Weight is weight. Water in the soil must drain, and the ground will lower when that happens. Kansai survives by turning that rule into inspection schedules, adjustable design, and long-term budgets. But every system that buys time has a price, and that price is not immediately visible. The first price is money. A sinking island never stops demanding maintenance. Every column lift, pavement repair, or seawall reinforcement becomes a continuing cost. The second price is dependence on data. Measuring wrong means reacting late. The third price is a shrinking safety space as the island lowers and the sea grows rougher. A meter of lost elevation is not just a number. It changes how waves meet the structure. The fourth price is psychological. The more famous a structure is, the harder small deviations are for the public to accept. People passing through the terminal usually see comfort, not the bargain being made underneath. When everything operates well, that very success makes the risk more invisible. But infrastructure risk rarely disappears. It moves into maintenance tunnels and technical reports. Some investments create no new image. They only keep the old image from tilting or failing. For an offshore airport, maintenance is not an appendix. It is an extension of the design. The more parts can be adjusted, the more procedures must be remembered, checked, and done correctly. The more sensors there are, the more humans must understand when data is truly warning them. Modern engineering does not remove judgment. It makes judgment more frequent. If settlement is underestimated, the structure ends up lower than planned. If overestimated, costs swell. Geotechnical engineering therefore always carries humility. Soil never reveals all its secrets in advance. A layer of mud beneath the bay can decide budgets, repair schedules, and flood resistance. This is the hidden cost of building offshore. The problem is pushed away from the city, but not erased. Noise moves away from residents, but the airport's weight is placed on an unforgiving environment. The sea does not object with complaints. It objects with waves, salt, wind, and corrosion. Salt ages equipment, wind tests barriers, and storms test every assumption at once. When every assumption is tested at once, one small weakness can become a major disruption. So Kansai's story is not only about sinking ground, but about a safety margin constantly being tested. For many years, the system worked well enough to make people believe everything was stable. Then a major storm arrived, asking nothing about the design, only how much the island could withstand. When Typhoon Jebi entered the Kansai region, the sea and wind became a real test at the same time. Waves did not merely strike the seawall. They climbed low spots, searching for gaps and weaknesses. Strong winds pushed water into the bay, raising sea level exactly when the island needed safety distance most. On the pavement, water began appearing where only aircraft wheels were supposed to be. Inside the terminal, lower levels became places where water could attack critical equipment. A modern airport can be struck at its least glamorous places: electrical rooms and drainage lines. When power, speakers, pumps, and transport are disrupted, infrastructure immediately becomes a story of organized survival. The storm showed that settlement does not stand alone. It meets storms, tides, and low-level design. What had once been a risk model became real water on a real floor. Outside, the bridge to the mainland was also tested, reminding everyone that an airport island cannot isolate itself. Even a well-operating island still needs routes for people, cargo, fuel, and rescue teams. When the connection weakens, the airport does not only lose runways, it loses its role as a gateway. Thousands of passengers can be stranded not because aircraft fail, but because the underlying system is overloaded. At that moment, the story was no longer about a structure sinking slowly, but about how it recovered after a fast blow. Mud answers slowly, but storms answer immediately. Kansai must endure both languages. After the storm, the water receded, but the questions remained in basements and barriers. Was the seawall high enough? Was equipment placed correctly? And was the flood plan realistic enough? A storm does not prove the airport useless. It proves that design conditions have changed. Standards that were once good enough may become thinner before larger new waves. What matters is that the airport did not disappear. It was wounded, then began repairing itself. That ability to recover reveals the true nature of offshore infrastructure. It does not need to be immortal. It needs to fail in controlled ways and be repaired quickly enough. In modern infrastructure, the ability to return to operation can matter as much as resistance. The storm turned a slow underground problem into a fast lesson on the sea surface. After that moment, the question was no longer how high to build, but how quickly to adapt. After the event, the first response was to look back at the places water had entered. Flooding revealed the real map of risk, clearer than many simulations on paper. Critical equipment had to be reconsidered. Should it be placed low for convenience or high for survival? Barriers were reviewed not only against the past, but against future storms that may grow stronger. Pumps and drainage were seen as a defensive line, no longer a minor detail. Emergency scenarios also changed, because an airport island needs an island evacuation plan. A bridge is not just transport. In a crisis, it is the island's umbilical cord. After the storm, the operational question became broader. How can paralysis time be reduced? Not every damage can be avoided, but closure time can be shortened. That is the new philosophy. Not only resisting nature, but preparing to recover after nature. With settlement, the response is the same. Do not wait for it to end. Manage it while it continues. Long-term monitoring becomes the island's memory, recording how the ground changes through each season. Each year, new data makes the model less blind, but never turns the future into certainty. Engineers learn to doubt their own predictions, because deep soil always keeps some surprises. From Kansai, other airport island projects learn that the ground must be treated like a partner. It is not enough to ask whether it can be built. One must ask how it will operate, upgrade, and pay its price. An initial site decision can follow a structure through its entire operating life. If built on soft ground, a project does not end at the ribbon cutting. It begins a long period of care. After the climax, Kansai was no longer just a bold symbol, but a lesson in technical humility. And that lesson breaks the biggest misconception about expensive structures. The common misconception is that the more expensive a structure is, the more absolutely stable it must be. In reality, money can buy research, materials, and maintenance, but it cannot buy perfect ground. The second misconception is that settlement means failure, as if the structure were collapsing immediately. The truth is more complex. Settlement can be predicted, measured, and managed, but never taken lightly. The third misconception is that simply raising the seawall solves everything. But water can enter through drains, basements, door gaps, low equipment, and forgotten weak links. Flood protection is not a single wall, but a network of small decisions working together. The final misconception is that engineering defeats nature through raw strength. At Kansai, engineering succeeds by listening to nature longer, more often, and with less arrogance. It does not command the mud to stop settling. It adjusts while the mud continues doing what it does. It does not force the sea to stay calm. It builds more layers of preparation for the day it does not. And that is the turning point. The most durable structure is not always the stiffest one. The modern shift is to design a structure as a system that can change over its own lifetime. Instead of only building higher, engineers must ask which parts can be lifted, replaced, closed, or restored quickly. Instead of trusting a single prediction, they build procedures to update predictions with new data. Instead of seeing maintenance as an annoying cost, it becomes insurance for the future. The airport of the future may not be a motionless fortress, but a body that knows how to adjust itself. Kansai reveals an uncomfortable truth. The harder the place, the more long-term care must be accepted. An artificial island does not become natural just because it has a runway and a terminal. It remains an artificial agreement with the sea, renewed through measurement and repair. In that agreement, the sea signs nothing, the ground promises nothing, and time can always rewrite the terms. The heavier the structure becomes, the slower the ground below answers, but that answer cannot be ignored. That is the lesson beyond Kansai. Engineering does not erase risk. it turns risk into work that must be done. One day, other coastal airports may also have to learn the language of settlement, storms, and rising water. Kansai is not a story of failure, but of the limits of believing everything can be locked in place. A great structure is not one that never changes, but one that changes before it is too late. In the morning, an aircraft rolls onto the runway, lightly, as if the island had never struggled. Beneath the concrete, the clay still compresses very slowly, like a wet mattress still sinking. Steel legs, seawalls, and sensors continue holding that giant table level enough. The aircraft takes off from the steel island, while below, soft ground quietly reminds us that engineering only buys more time.